Everyone's slowly trickling in. We'll get started here in just a moment. I can still see some people are joining in really quickly. There we go. All right. Good morning, everyone, and welcome to Groundwater 101 week. We're thrilled to have you here today. Today's session will explore Python and FloPy workflows for groundwater modeling. And we're excited to welcome our speaker for today, Chris Langevin. And before we dive in, just a quick reminder, our sessions will be recorded. You will receive a link to the sessions after the event. The slides will also be provided by speakers, and they'll be sent to all of the attendees. We also want to highlight the upcoming WGC conference coming up in San Diego from October 6th through the 9th. Early bird registration does end on August 8th, so make sure to sign up soon to take advantage of the discounted rates. Also, we want to have a special thank you to our annual sponsors for making events like this possible. And thank you for all of our attendees. Thank you for joining us today. And our session sponsor, WSP as well. And Chris, I will give you the floor.
All right, sounds good. I'm going to go ahead and share. All right, I assume everybody can see that?
Yep, you are good.
All right, so my name's Chris Langevin. I'm a hydrologist with Papadopoulos and Associates. That's relatively new for me. I've been there a few months. Prior to that, I was with the U.S. Geological Survey at our headquarters office. I was with the USGS for about 27 years and just decided to do something different in light of the changes that were coming down. So it's a pleasure for me to talk to you today. Um, I'm going to talk about Python and FloPy workflows for groundwater modeling. This is something I've been working on for quite some time. It's going to be it's going to be very introductory. So I'm not going to assume that people are very familiar with Python. Certainly MODFLOW, but maybe not Python. And I'm going to try to go through it slowly. So I recognize some people may not be familiar with Python and how it works and how you might use it for groundwater modeling. So I'm going to try to emphasize that today. And also feel free to interrupt me. We can make this as interactive as you want. So feel free to interrupt and ask questions. So in my previous life, I worked in Florida I was down there for about 10 years and I did graduate school down there as well. And I encountered some work by these guys, Henry and his student Haliki from the University of Alabama. And they were looking at groundwater flow in the Florida carbonate platform. And they did some work back in the early 70s, excuse me, in late 60s that I found really interesting. And one of the things that they did was build this laboratory tank. And I talked about this at the last MODFLOW conference, so this may not be new to some of you, but they built this really interesting tank to sort of pattern what might happen, what sort of flow, groundwater flow system would we expect in the Floridan aquifer system. And so they had on the left side a freshwater storage tank that went in at room temperature. And on the right, they had cold salt water that was sort of assigned as a constant head boundary to represent the interaction of the Florida carbonate platform with the ocean. And then on the bottom, they had these adjustable heaters so they could heat this thing up because in Florida, there are some springs suggesting that there was a source of geothermal heat in the middle of the platform. And so they were just trying to get a feel for what groundwater flow patterns might look like in the Floridan platform. So they published this work. I think Jeff Haliki wrote his master's thesis on this, and they wrote a report and they talked about some of the flow that they saw or were expecting to see in this tank, though they couldn't see it exactly, but they tried to do some tracers. And so they would get a little bit of a feel for what might be happening. And so one of the things that I've looked at over the years is how do we simulate a system like this with MODFLOW-based codes? It's something that I worked on with CWAT and then now also with MODFLOW 6. And so I'm just going to show you, I'm going to start off with an animation here to show you the result of a MODFLOW 6 simulation that shows groundwater flow and particle tracking in this top panel. So this is a cross-section model of the Henry and Halicki laboratory experiment. We're starting with all salt water in this box, and where you're going to see fresh water come in on the top left. And we're also simulating heat transport in this box. And so we have these heat sources along the bottom. And this was used primarily to demonstrate MODFLOW 6, but I'm also showing it here because all of this is done with FloPy and Python workflows. And I have to put out a big advertisement just for the way you can work in building models using Python in particular and FloPy. It's reproducible. It takes some work to get it set up. You have to be good at Python. But once you become familiar with this environment, it's really nice the things you can do. So let's go ahead and start this up. So we've got where you're going to see particles coming in along the top left, representing fresh water, and along the right, representing salt water coming in from the boundary. In the middle panel, you see fresh water infiltrating into the box. You can see some sort of waves of these geothermally driven convective currents, as well as the heat transport. You can see the heater on the bottom left was adjusted to be hotter than the ones to the right. And so we're essentially representing this physical experiment that was done in a laboratory with MODFLOW 6. Now, one of the unique things about MODFLOW 6 is we can have these multiple models, we call them, a flow model, a salinity transport model, and a heat transport model, all running simultaneously in the same simulation, and there's feedback between them. So the particle tracking capability is something relatively new to MODFLOW 6, and it's also another model that you can activate in a MODFLOW 6 simulation. So this has been the culmination of a lot of work that we've done with MODFLOW 6, and I think it nicely demonstrates this ability to have multiple models running. And I guess more importantly for this particular presentation, all this is done with Python and FloPy and the pre-processing and the post-processing. All right, so what are we going to do today? We're gonna I want to walk you through how to install and use the Python FloPy package for working with MODFLOW-based models. We're going to develop some simple groundwater models from scratch. I have a number of Jupyter notebooks that we're going to download and take a look at. We'll see how far we get. And we're also going to show how you might load an existing model, be able to pull out the hydraulic connectivity and look at and visualize it or look at statistics on it. So just get a feel for how this works. In 2 hours, this is more of a demo than a full workshop for becoming proficient. This is just the start. Hopefully, you'll see some things that you like and will realize it might be worth the investment of moving forward with it. So, got a quick presentation here, talk a little bit about MODFLOW and FloPy, and then we'll move into this live demonstration. Talk a little bit about Conda environments, Jupyter notebooks. Git MODFLOW is a utility that comes with FloPy that you may or may not be aware of, and then we'll look at some examples. So Prior to joining Papadopoulos and Associates, I was in the USGS headquarters office, initially in the Office of Groundwater, and so I was the caretaker for MODFLOW there. So I've had a lot of experience working with the different flavors of MODFLOW, and it's something that I was really proud of to work on. You know, it's been around for 40 years, and there's not many software packages that have been around that long. It's a community model. You know, everybody's familiar with it that does groundwater modeling. Um, I think it's really well designed, and it's designed to be modular. And one of the things that we've emphasized at the USGS is that it's teachable, right? People can pick it up. The concept of packages is really natural. You turn on packages you need, and you don't worry about the ones you don't. MODFLOW's portable, runs on lots of different computers, from Raspberry Pis to supercomputers. And it's extensible. People have been able to pick it up and extend it to do all sorts of things. It's well documented. And, you know, for the most part, over that 40-year period, it has received stable funding, primarily through federal sources. And even in light of the changes that we see today, it's still going strong at the USGS. So there's a number of the way we would think about MODFLOW, at least in headquarters, is we would have a core version of MODFLOW that we would put a lot of care and emphasis on maintaining, going all the way back to the 84, the initial version, 88, 96, 2000, 2005. And then when I joined the USGS Office of Groundwater back in around 2010, we started on the version that's out now called MODFLOW 6. And so we see these as sort of the core versions that we see as enterprise versions of MODFLOW developed by the USGS. But there are also lots of other variants that many of you are going to be familiar with. There's MODFLOW Newt, which is very popular, perhaps even more popular than MODFLOW 2005 now, or even MODFLOW 6 for that matter. There's MODFLOW USG, which many people are familiar with and use, I know in California, quite a bit. CWAT is a program I worked on when I first started at the USGS. It's a combination of MODFLOW and MT3D for variable density flow and transport. I know many people in California in particular use GSFlow, and there's just a wide variety, LGR, groundwater management, modeling version of MODFLOW, conduit flow process, MODFLOW ohm, and so forth. And so the way we would sort of visualize these different versions of MODFLOW and variants is, as these variants would pop up, we would look at what was successful in these variants, and over time we would try to pull from the variants some of these newer capabilities and bring them into the core version. And so that's kind of been this development path for MODFLOW at the USGS. So some of the highlights in this latest version, which you know, something I've put a lot of work into over the past decade or more. We have these multiple model types. It showed you that animation: groundwater flow, solute transport, heat transport, particle tracking. We can do structured or unstructured grids. We have some incredible parallel computing capabilities now. We have the application programming interface, and we're not going to go into any of these things, but while MODFLOW is running, you can actually go into the code while it's running and make changes, or maybe you have your own package you want to develop for MODFLOW. The API is a nice way to do that. And we have lots of other things that are on the way. Here's a paper that just came out that talks about some of these concepts. Here's a figure showing this parallel version of MODFLOW for the continental US, where it's just a one-layer model, but we've divided the continental US into a certain number of models, and then we solve them in parallel on a supercomputer. And so this is now available in MODFLOW 6, this capability to solve multiple spatially variable models in parallel. One of the neat things about MODFLOW is that it applies at many different scales. So people use it for benchtop applications, just looking at flow through a Darcy permeameter, to the site scale, the sub-regional scale, regional. And now we also have these national as well as global models of groundwater flow. And so it's been really interesting to see MODFLOW applied at so many different scales. So let's get into a little bit of the nuts and bolts, and presumably many of you are going to be familiar with these concepts, but when I finished graduate school, or when I was in graduate school and even undergrad, there are graphical user interfaces for running MODFLOW. Groundwater Vistas, Visual MODFLOW, GMS, Model Muse, and I think I've used them all over the years, and they're really nice. They allow you to visualize where your boundary conditions are, point and click and make changes to properties and add boundaries and quickly run the model and visualize results. What I'm going to talk about today is the FloPy Python package approach, where you write a script that generates the model input files. It can run the MODFLOW model for you as well as post-process the output files. And then probably many of you are also familiar with just working with these files manually. And it's something that we emphasize in the MODFLOW classes that we teach. Just the ability to work with the MODFLOW files directly, run the model from the terminal window, use GIS if you need to build some of the input files or spreadsheets or write your own custom programs. I see a lot of people still out there using Fortran programs to write recharge arrays for MODFLOW. I would, that's fantastic. I would say Python is also a really nice option for doing that. So we're going to be focusing on this middle option here. But for those of you familiar with MODFLOW, which I think most of you are, this is sort of the simulation workflow. We have a GUI or maybe FloPy, and we generate these input files. And then we run MODFLOW, and MODFLOW is a separate executable program that then reads these input files and generates its own output files. And then we use something else to read those results back in and post-process. So it's amazing how many people sort of overlook this. When you're using a GUI, it's easy to think of the GUI as being MODFLOW. But really what the GUI or FloPy or however you're working is doing, what it's doing is building these input files. You run MODFLOW separately, and which generates output files, which you then look at. So what is FloPy? Now, FloPy is a Python package, so it's written in Python. And we consider it a pre and post processor for a variety of MODFLOW-based models. One of the most important things is that it requires Python expertise. Python is a programming language. So, we've taught quite a few classes on FloPy and how to use it. And if you have not programmed before, or you've not programmed in Python, FloPy sounds really cool, but then when you start using it, you can hit a wall pretty quickly because you have to become proficient in Python in order to use FloPy effectively. So that's a very important point. You're going to see some syntax today, and it's painful at first. I think I started using Python back at around 2006 or so, and it was a very steep learning curve. And I persevered through it, and I'm really glad I did because it opened up the door for all sorts of things. FloPy has full support for MODFLOW 6. We do some unique things with FloPy, in particular for MODFLOW 6, that allows us to support anything and everything that's available in MODFLOW 6. That's not necessarily true for the other versions of MODFLOW, but it is true for MODFLOW 6. FloPy has a number of tools for building different grid types. You might see a little bit of this. There you can export models in a variety of different formats. You can export to shapefiles, netcdf files, VTK. There's a variety of exporting capabilities. One of the things that FloPy is used quite a bit for is just plotting, and that's probably what you're going to see a lot of today. And I should mention that we use FloPy extensively in our MODFLOW 6 development. So going all the way back to when we first started MODFLOW 6, we were developing models with FloPy and running them with MODFLOW 6, and we continue to do that to this day. So just to give you a little history on this, here's the FloPy family tree. I guess we've got quite a few people making contributions to the FloPy code base over the years. It goes back to a couple of our colleagues, Mark Bacher and Vincent Post, who sort of started this and worked on the initial version. And then around 2010, at the USGS with my colleagues Joe Hughes and Jeremy White, we sort of took over FloPy to a certain degree as we started working on new versions of ModFlow, and from then on we had lots of different contributors working to extend it and make it as usable as it is today. There's a few publications out there. It's amazing how many citations these get, in particular this 2016 version, where we just sort of talk about this concept of scripting ModFlow model development. It's a different way of working. One of the nice things about this approach is that you can automate everything. And while it may take some effort up front, it really pays off in the long run. So if you need to run your model 100 times for some reason, and there are many different reasons you might need to do that, or if you make a change and you want to run the model from start to finish and get all your plots at the end, it really pays to automate that full process. If you find a mistake at the end, you can go back and run something from start to finish, and you quickly have the latest results. So I can't emphasize enough how much this workflow has sort of saved my butt and many of the people I work with, just this ability to rerun everything quickly and efficiently through the automation that this affords. So there are a variety of these ModFlow variants or flavors, and this is just to give you an idea of sort of the support status. You know, how well does FloPy work with these different codes? ModFlow 6 is fully complete, as I mentioned. ModFlow 2005 is very good, I would say. Newt is also very good. ModFlow USG is good and getting better. People are using FloPy for ModFlow USG. And so we have some examples and talk about that. MT3D as well as MT3D USGS, we have quite a few example problems that demonstrate how FloPy can be used to pre and post process for MT3D. CWAT is similar, and then also ModPath, so is also very good. So there are other flavors of ModFlow that are not listed here that may or may not work with FloPy. Maybe you could use it for some packages, but not others. But these are sort of the core ModFlow variants and flavors that FloPy is developed for. So one of the things that we've done for ModFlow 6 support in FloPy is, as I mentioned, support every single package and model type. As we develop new models, like the particle tracking model, hand in hand, FloPy is updated to support these new models. And we've also put some effort into designing different types of grids directly from FloPy. So we call these a regular structured grid, which most people are familiar with, a grid consisting of layers, rows, and columns. I think B is an example where we can change the spacing, the del R and del C spacing. We have, let's see, this one in D here is a what we would call a quad tree grid. There's a program that the USGS distributes called GridGen, which can generate a mesh like this, and FloPy can call that mesh generator and create a grid, and then you can use it within FloPy to build your model. Here's an example of a LGR type grid where in ModFlow 6, this might be two different models, where we have an outer regional model that has this cutout where we have a finer model inside, and these two models can be coupled tightly and pass flow between them. Here's a triangular mesh and a Voronoi grid. So these are all different types of grids that you can generate within FloPy. I'm not sure we're going to get into these today, but there are plenty of examples for how to generate these and how to build models with them. I just want to make this point. If you are not familiar with Python, um, Python is zero based. And so it can be something, a hurdle for many people coming from working with MODFLOW. So in FloPy, the way it works is when you're working in Python and with FloPy, everything is zero based. FloPy makes the conversion. ModFlow requires one base numbers to run. And so FloPy converts it upon writing input files into one based. And for the most part, when FloPy reads results back in, it converts it back to zero based. So we've tried to keep that separation distinct so that if you're working in Python and with FloPy, you're using zero base numbers. This is column 0 here, column 1, column 2. Although there are 9 columns, this is actually column 8. This is row 4, even though there are 5 rows. So I just want to point that out because that is something that might take a little getting used to, but ultimately that sort of becomes second nature. There are quite a few examples of using FloPy to build models. I'm sure many of you have used FloPy to some degree, and hopefully you found these. But there are a lot of examples for generating meshes, for how to intersect spatial features with your model grid. I should also mention on the ModFlow 6 side, we have quite a few, I forget how many, probably over 100 different examples. And they all are built with FloPy. And they do all sorts of things. And here's a few examples. But so there are quite a few examples for hopefully you can find an example to help you do what you want to do with FloPy. I should put out a plug. Python is sort of it's revolutionized my workflow. This is Guido van Rossum. He's a Dutch guy who came up with Python. Um, it's really nice. I can't say enough good things about it because it's so popular. There have been all these packages that have popped up, and really you can find something to help you do just about anything you want to do. Um, FloPy is a package now that is easily installable, and we're going to talk about that here in a minute. But I can't say enough good things about the Python workflow. Conda is another integral part of how we work. Conda is a package manager. It's generic, but we use it specifically for managing our Python packages. And there were some instructions that went out just yesterday, so I recognize probably not many people got to it. But the nice thing about Conda is you can install what's called an environment that has a collection of packages for whatever you want to do. And so I sent out sort of the recipe for the Conda package that we're going to use for the remainder of this workshop here. But Conda then it looks at this list of packages and it builds a containerized environment that you can use, and you can just delete it when you're done with it, or you can keep it around if it's useful. But it's a way to have different collections of Python packages installed on your machines, and you activate the one that you want to use. So in this particular case, there's a star next to this GRA25 FloPy. And you see here in front of the command prompt, there's a GRA25 FloPy sort of in parentheses here to indicate that that environment is active. And it gives us access to the packages that we're using for this particular workshop. I've also put together a GitHub repository that has the notebooks, this environment, and essentially that's it. So we will have a record of what we go through now. And you'll be able to look back at these notebooks. You can download this whole repository and be able to run through these things that we do today. And I'm going to sort of walk through showing you how to get up and running with this repository in just a minute here. Okay, so let's see. That was a half an hour. Do we have any questions about that before we move on? I'll give you a minute here.
Hi, it just says one, I guess, question kind of. I didn't receive the instructions. How can we get them?
Okay, we will we'll go through it right now from scratch. So um I don't know if I ask a question? Did anybody get the the environment installed and running? And if not, it's no problem. You can just be passengers today in a 2-hour workshop. I'm happy to just walk through it.
I have installed it.
Okay, great. All right. So it looks like a few people did. Wonderful. And some people have problems, but which which can happen, of course. So when I can tell of maybe it's not that funny, but we think it's funny now. You know, we've taught Python and groundwater modeling workshops for quite some time. And back when we first started, everything was very fragile. And so the first half day of the class, it was often a week-long class, would be airing up the grievances, we would call it, where we would have to work through installation instructions. But with these Conda environments, things seem to work quite a bit better, and we'll try to go through that now. So just to give you a heads up, I'm primarily a Mac guy, though I do have to go back and forth between Windows and Mac. I'm going to get started over on the Windows side. I have a Windows virtual environment just to get people up and running, recognizing that most people use Windows, but I may cut back over to Mac um, just so just because it's easier for me to work in that environment. So, all right. So I saw some chats about people using VS Code as opposed to Jupyter notebooks. That's just fine. If you can get this up and run, however you want to get this up and running, um, VS Code is my preferred way to do it. If you've never seen Python or Jupyter notebooks before, I think this Jupyter Lab approach is a bit easier. So let's go all the way back to the beginning. And if we just go to this, if we just go into some search, open up a browser, and if we type Langevin GitHub GRA 2025 and hit enter, we're looking for this GitHub repository. Christian Langevin, FloPy 101, GRA 2025. And if you click on that, it brings you here for some reason. There's no security policy. I've never seen that before, but we want to look at the code tab here. And you should see something like this. And I'm going to go ahead, I'll paste this into the chat real quick here so everybody can see that. So if you can't find it, you should be able to click on that chat link. Okay, so next, one of the things in the instructions here, in the instructions at the bottom, there are some instructions for how to install Python and Conda. so that you can create environments. And we can just take a quick look here. And if you haven't done this, you might not have time to do it right now while we're doing this live. You can give it a shot, but it might take a couple of minutes to go through this process. So maybe you just want to follow along, just watch. But MiniForge is a flavor of Python that comes with Conda. You can download an installer for it. And then there's instructions here for creating this environment.yml file. And I'll just go ahead and do that real quick. So so if you've installed, after you install MiniForge, you can just type in MiniForge and you should be able to find this MiniForge prompt here. And it looks something like this. And you can see here it says base in front. This means that it's Conda aware, and all the paths are set up to install environments. I think we can type Conda, for example, minus version, and it tells it found Conda. One thing you can do is you can type Conda env list, I think it is. Conda env list will tell you what Conda environments you have installed. You can see I have a few. I also have this GRA25 environment that we created. And so let's say we want to get up and running. I'm going to change directories into documents, though you can work wherever you want. dir, and let's just make a new folder. What do we want to call it? A new folder in documents. And let's just call it GRA25. How about that? So we're just creating a new folder called GRA25, and that's where we're going to work today. Let's see. So in GRA25, let's go to GRA25. Let's make a new environment in there, a new environment list of packages we're going to use. I'm going to create a new document and I'm going to call it environment.yml. Now I'm just going to create this manually, but you could download the one that's on this repo, or a lot of times they're provided. FloPy comes with one. But I'm just going to walk through this how you install an environment. It's really pretty simple. And let's see, can I open this with I'm going to start a Notepad++ here. Oh, there's an older one. And I'm just going to open this environment file. And I'm going to go back to this. I'm going to go back to this repository. And I'm going to click on this environment.yml file that I've posted in this repository. And I'm just going to copy the things out of there. I guess I can just copy this here. Copy the file. If I paste that in there and hit save, this now is the list of packages that will be installed when we say Conda, install this in this environment. So what Conda does is it says, hey, you need FloPy. You said you want FloPy. Well, FloPy also needs a bunch of other things. It needs NumPy, Matplotlib. So Conda says, hey, you need FloPy. FloPy needs these other things, and it builds a list of everything that it needs to install in order to make sure all these dependencies are there for you to work. And so it builds this dependency tree. It finds everything that's compatible, and it installs it into that environment, and only that environment. So when you delete that environment, everything that you've installed for that environment is gone. It's really nice. You can create these things in 5 minutes and blow them away if you don't want to use them anymore. So they're great for experimenting. So the way this then works is it's in there. You say conda env create. And by typing this command here, it automatically looks for, let's see if I can do it. I already have this one created. It says it already exists. If you hadn't installed this already, it would go out to the web, pull down all these dependencies and install them into this environment. If you've done that, conda env create, you can now say, when we've done this already, conda env list, and you'll see this GRA25 FloPy. So at this point now, you can see that the base environment is what's active, but we can activate the environment that we just installed by saying conda activate GRA25 FloPy. And you'll see now that we have this parentheses in front telling us which environment is active, and you should see something like that. I'm going to look at the chat real quick just to see if there's any questions so far. I don't see any. Okay. So at this point, we're working in this folder, GRA25. We have our conda environment activated. If you're working in Visual Studio or VS Code, you should see this GRA25 FloPy environment available to you. If you're, yeah, you should see that available. If not, we'll do it this way through this activate. So at this point now, we can start up Jupyter Lab. But before we do that, let's do one other thing. This environment, you'll see that we created, had something called Git installed with it. So Git is a source control software that we use quite a bit as MODFLOW developers, and hopefully many of you are familiar with it. It's an easy way to pull down repository content. So I'm going to go back to this sort of landing page for this repository, and I'm going to click on this code button, and I'm going to copy this line right here, or copy it with this clipboard thing here. And because we're in this GRA25, I can say git clone and then paste in that repo address, and it'll go out and it'll pull down everything that's in that repository. And so at this point now, you can see in our GRA25, it pulled down the repository. In there, we've got some things, we've got everything in the repository, including a collection of notebooks that we're going to go through here in a minute. Okay, so we're in this GRA25. I'm going to change directories into that FloPy one. I'm going to cd FloPy 101. I'm going to go in there. And at this point, I'm going to start up a Jupyter notebook, hopefully, and there are no airing of the grievances. And we'll see if we can get off the ground here. So one of my favorite ways to run these notebooks is with Jupyter Lab. You type Jupyter Lab, and what that's going to do is going to fire up the web browser in the background and open up something that looks like this. And hopefully some of you have managed to keep up to this point. If not, I think it's still really helpful just to sort of see this process so that you understand the concept of environments, what that means, how that's different from Python. a Jupyter Lab now is some software that allows us to run notebooks in a web browser. And so when we open up, when Jupyter Lab opens up, we have this little browser here on the left. That's like a file manager. We can double click on it and we can open files. I think we can even edit them in here. We can navigate down into different folders here. And we can start up these Jupyter notebooks. Does anybody have any questions about this so far? Anybody still there?
I don't see any questions in the chat at the moment.
Okay, great. All right, so if you've made it this far, this is now where things start to get fun, I think. So let's see. I wanted to mention one other thing here. Let's see, did I want to mention that now? So we've worked with Conda. We're getting set to run Jupyter notebooks. I want to mention this Git MODFLOW capability. I'm going to start up another mini forge prompt here. No, actually, I'm going to do it over here. I'm going to start it up over here. So so hopefully you see something like this. We can click on this terminal and it'll start up. It's going to be PowerShell. Dang it. Let's see, I'm going to close that. See, is there I'm going to do it a different way. And you don't have to do that. Well, you might have to do this. We'll see. Mini forge. Let's say Conda activate GRA25 FloPy. If you once you have this environment active, you can type git modflow, and I'm going to just type help with it. Git modflow is something that FloPy installs, and it's available because FloPy was installed. That will allow you to go out and it'll pull down all the different ModFlow executables, all the latest versions. We build all these different ModFlow executables and make them available, and it'll pull them down. And there's different places then where it can put them. So just to show you how it works, let's see if I make a directory called, I think I already have a test. How about ModFlow exe? cd modflow exe. And if I type git modflow space and dot, it means put them all here. So if I type git modflow dot, it goes out and it pulls down a zip file with all of these ModFlow executables, all the latest versions. It has ModFlow 2000, 2005, a double precision version of 2005. This works on Mac, Windows, and Linux. It's an easy way for you to pull down executables and right away start using the latest version of all these different executables. Now, one thing that may happen to you when you try to run ModFlow in these Jupyter notebooks is it's going to say, I can't find ModFlow. So what you can do is you can type git modflow, and there's some syntax here. I'm just going to go back to this. I'm going to go to FloPy. I'm just going to show you where this is. You don't have to go there yourself. But under the FloPy page, there is some discussion about git modflow, and there's docs for how to use it. And one of the things you can do is you can type git modflow space :Python, and it will install it it'll install all these executables in the environment that you're working in. So if I do this right now, it'll do what I just did. It'll go out, pull it all down, and it'll put them into this GRA25 repo. So whenever that repository is active, it can find all of those different versions of MODFLOW. And let's just see let's see if it can find that MODFLOW 2000. It might have other versions, so we'll see if it can find it. Yeah, you can see that it put a copy of MODFLOW 2005 in this MiniForge GRA25 FloPy environment. So this is kind of a cool little capability that it's a little gem that comes with FloPy that you may or may not be aware of. Okay, so let's go back to our Jupyter lab, and the first thing we're going to do is let's open EX01 TICE, and let's just double click on that. So this is what a Jupyter notebook looks like. We can have comments. These are markdown comments, or we can have live Python code in there. And so there's a typo right there. Construct and test the TICE function. So the way it works is if you hit Shift Enter, it'll execute that cell. If I hit Shift Enter on this first one, it doesn't do anything. If I hit Shift Enter on this one, it actually will run that Python code in that cell. If we want to add a new cell, we can say, hey, let's add another cell here. And now we can just enter Python commands. We can say x equals 10 and print x. So this is where, at this point, you have to understand Python syntax. But these notebooks are a great way. They're interactive. If we make plots, they show up right in the notebook. You can document and put equations. You can document a full workflow to do something. So this first example is showing how it's not FloPy, it's not going to build a groundwater model, but it's going to show you how you could use a Jupyter notebook to look at the TICE function to calculate drawdown. So let's just go through and run some of these cells and see what happens. So it turns out that for those of you groundwater people, I'm sure you've encountered the TICE equation, and the TICE equation gives us drawdown. One of the components of it is the well function of U, and it turns out there's a version of that in SciPy, in the SciPy special package called EXP1, which actually calculates the well function of U for us. So we can run this. In this particular case, we're making a function here that will calculate the drawdown for whatever we pass into that function. We can pass in our pumping rate, our transmissivity, the radial distance, the storage coefficient, and the time. And then we can use that function to calculate drawdown. So in this particular case, we set our parameters, we pass it into the function, we get back the drawdown, 0.61, whatever units we're using. Then, once we have this function, we can call it in loops and do different things. So here, let's say we want to do a distance drawdown plot where we look at drawdown as a function of radial distance from a well. So we can do a loop where we go, we change radius from 1 to, 100,000 by every 1,000 units, meters or feet. And then we call that TICE function, and we store in X we store the drawdown, and in Y, or in X we store the radial distance, and in Y we store the drawdown, and we can make a quick plot of it. Pretty straightforward, but it is new syntax if you're not familiar with Python. And we can instead of doing distance drawdown, we can do time drawdown, go through and pass in different times, accumulate things and plot them. So this is sort of a common workflow in Jupyter notebooks for doing hydrologic analysis. This isn't groundwater modeling yet. I guess it is in a form. It's a mathematical model of groundwater flow. So Python, and now actually we're using the NumPy package for doing array manipulation under the hood. Instead of passing in and calling the Tice drawdown function over and over again for each time, we can actually pass in a list of times and get back a list of drawdowns. So we can make this call in one single call. Our function now will automatically iterate through everything we pass in and return a list of drawdowns or an array of drawdowns instead of doing them one by one. That gives us some powerful capabilities. It's called broadcasting. That if it can, our functions will be able to process entire lists of information, arrays of information, instead of just individual values. So why might we want to do this? Well, let's say here's an example where we're gonna try to calculate drawdown and make a map of it. So let's just do here we're calculating x coordinates from 0 to 10,000 every 20 units. Y coordinates, we're making a grid out of them. So we have a grid of x coordinates and y coordinates. And here we're actually contouring the y coordinate value. Not very interesting. It's just an example to see what's happening here. But more importantly, what we could do here is we could say, hey, we have a well at 2,500, somewhere right in this point. Using broadcasting, we can actually calculate the radius. This is going to calculate the radius to that well at every single point in our grid. And we can make a plot of that. So this is R now is the radial distance at any point in our little domain here from the well to our point. So that's hopefully you can see where this is going. We now then can extend this. Now that we have the radial distance from the well to our point, we can use that with our Tice function. And we can calculate Tice drawdown for any point in our grid. Because here we calculate the radius, which is a grid of points. And we can pass that radius, that grid of radial distances to the well, into our Tice drawdown function. And because of broadcasting, this concept of broadcasting, it gives us back a grid of drawdowns. Okay, so that's kind of cool and kind of powerful. I don't know about you, but I guess in grad school, I had to look up well function values in the back of the textbook. So this is a real nice advance over some of those old Tice calculations that some of you may have done. All right. So now what if we want to take it to another one step forward and, well, how might we animate this? Let's see if we can do that. Well, Python has some nice capabilities for creating animations right in the notebook. So what we can do, we have, just to briefly explain how this works, we sort of set up a base, the base properties of our animation in the top here. We then provide a function that will draw whatever we want for each frame. So I is essentially the frame number that we're going to draw. And this animation syntax here essentially is calling our function over and over again, creating images and stitching them together. And if we run this in the background, hopefully if this all works, it should create an animation for us right in the notebook. And you should see something that looks like this. This is, you'll see we're drawing, I mean, we're essentially drawing everything, but we're using some Python and Matplotlib animation capabilities to animate this. And now we should be able to hit the play button and show an animation of, in this case, Tice drawdown with time. So this is included here just to really hopefully crisply show these nice capabilities that come with Jupyter notebooks and Python and these animation capabilities that as you'll see as we move forward, we can use them in our notebooks for modeling as well. Okay, so let's go one step further now. So let's say we have this simple cooked up example. Well, let's say we have a bunch of wells in our domain and we have different pumping rates for them. It looks like this. They might be in a spreadsheet. They might be in a text file. In our case, we just put them in this text string called well text. We have the well name, the X and Y coordinates, and we have a pumping rate. Well, there's some syntax here for showing you how we might parse that string into a list of things. And our list, our well list has the well name, the X and Y coordinates, and the pumping rate. We can then make a function that'll get the drawdown for our list of wells for any time and using the grid that we want to plot it on. So in this particular case, let's see if we get something back here. So we made this simple function where we pass in that list of wells. It goes through each well, calculates that radial distance for every point in our grid to that well. It calculates the drawdown for that well, and then it accumulates it. So using the principle of superposition, we add up all these drawdowns and we end up with a single map of drawdown from all these wells for our entire domain. So, I mean, this is pretty cool. With just a little bit of Python code, we're able to stitch together and do some things that I would say are pretty powerful. And once again, we can animate this same exact thing, except we're animating the results for our list of wells, which is just a fabricated problem, and animate the drawdown from that, from those calculations. And though it's commented out here, right now we're showing this animation in our notebook, but you could also save it to different formats and use it in presentations or however you want to use it. Let's take a look at that. So this is an animation of drawdown from these multiple wells, all with different pumping rates. Okay, so that's example one. Any questions so far?
A quick question.
Yeah.
Is the color scale related to the meters of the drawdown? Is that it?
The color scale is related to the draw, yes, to the absolute draw values. That's correct.
Okay, thank you.
Yep, good question. And I didn't do it here, but we could add a color bar, to indicate what those actual colors represent. But yeah, so we have the most drawdown at the well locations, and it's spread and the effects of pumping spread out over time, subject to all the limitations and assumptions in the Tice equation, which there are many. Okay, so let's so what I'm going to do is I'm going to go ahead and save these. If we make any changes to them in the repository, I will put up the completed versions of all these things. And if we make any changes, then they will have been run. You'll be able to go to that repository in the future and look at them if there's anything that we do of interest here today. All right, so I can save this. I've saved this animation, and then I can say close and shut down notebook. Okay. All right. So the next one, the next notebook, we're gonna make from scratch. And we're gonna just see if we can get a FloPy model running as quickly as possible. I'm gonna show you how to do that because this is how I start out this way a lot, just to make sure I can run a model really quickly. So let's just create a new notebook. And a lot of times, what you need to do is I think you may need to save it. Let's see, file. Let's see, save notebook as, and I'm going to call this, what did I call it? EX. You can call it whatever you want, but I'm going to call it EX02 underscore quick start. I think that's what I called it on the front page there. Sure, well, I'll save it. Oh, okay, we have the other one too. So we have this new notebook here. Let's go over to FloPy, to the FloPy website. I'm just going to type in FloPy. Usually comes right up. And if we just scroll down on this FloPy website, there's something down here called Quick Start. Now, we can just copy this. If we copy this or hit this copy button here, we should be able to copy this Python code and go back to our, I've got something covering up. Go back to our quick start and paste it in there. And if we hit Shift Enter, hopefully something happens. And for me, this is what I see. A lot of things just happen there. So let's walk through what we just did. We essentially just use FloPy to build a model from scratch, run that model, and post-process it. So we call this the quick start because it's the minimal amount of code to actually generate a running model with FloPy and show some results. So with just a little bit of Python code, FloPy, and MODFLOW installed. A lot of times, if you've tried to install things and run it, a lot of times what'll happen is it'll say it can't find MODFLOW. So that's why that get MODFLOW is an easy way to get up and running. And have MODFLOW installed, you can install it. Like in our particular case, it found the one that's in our GRA 25 FloPy environment. So you can install, all these MODFLOW versions right into the environment. So they're available for you. And then, it has CWAT and MT3D and all these other things too that you might want. It's a quick and easy way to run these examples and get off the ground running. Okay, so let's talk quickly about what happened here. So what we did, and so this is a MODFLOW 6 simulation. So what happened is we created a MODFLOW simulation. This is the syntax here. We created a temporal discretization, our iterative model solution, our solver, and we just used default values for many of these things. We created a groundwater flow model, a discretization package, initial conditions, our node property flow, our constant head. We put constant heads at cell 000, which is really cell 111 in one base numbers. We put another constant head in cell 099, layer row column, layer 1, row 10, column 10. So we put a constant head here and here. And we essentially just forced flow through this simple box. Yeah, that's about it. And what it did, what this code does in the background, you can see we said WS is shorthand that we typically use for workspace. So it created a new folder here called My Model, and it generated the input files. And after we ran it, we got the output files also in this folder. And then we were able to, FloPy has some nice capabilities for reading all of the output from MODFLOW. So when MODFLOW runs, it creates a variety of text files and also binary files. And FloPy comes equipped to read all these different things. And it even has some shorthand ways to say, hey, give me the head back. And this command here goes into the model itself, goes into the binary file that MODFLOW wrote and pulls out the heads. In this particular case, for the last time step, there was only one time step, but by default, it grabs the last time step. It also gets out from the budget file. It can also get data out of the budget file. In our particular case, we can get out specific discharge components. MODFLOW 6 can save specific discharge to cell centers. And that's what this code is using to plot these vectors for each cell. So there's really a lot going on, but we've tried to set it up so that the defaults are hopefully useful to at least get things up and running relatively quickly. Okay, so we're about an hour and 10, 15 minutes in. I'm just gonna keep on going here.
Chris, there is one question in the chat though.
Okay.
Question is, are all the packages in a given environment separately installed? If so, is there a way to have Conda look for already installed packages in other environments to save disk space? Or is it just about being sure to delete the environments?
That's a good question. And so in general, I would say the answer is all it installs everything into that environment. So now the packages themselves are pretty small for the most part. So when you install an environment, I haven't done it lately, but I don't think they're very big. Um, so I've never had a problem with disk space. So I just, will create as many environments as I need. They do get old. All of these packages are changing rapidly with time. So for what I found, it makes the most sense to just wipe them out and reinstall them as you need them and get the latest versions. But yes, that's a good question. Okay, so let's go ahead and so right now with this quick start, we just created a MODFLOW model from scratch very quickly, hopefully without too much pain. I'm going to save this. And there's different ways to close this, but I just say close and shut down notebook. Okay. And if you see these little dots next to things on the left, that means that that notebook is running. I think, let's see if I can close this. Is there a way to, let's see if I shut down that kernel. This guy was sort of running in the background. There's really no downside to that, but just to be in control of what's running. It's good to know what notebooks are running. They can take up some resources. So let's go to the next one. So this is an example based on the quick start. Now this one is I think the notebook is all filled out, but we'll just sort of walk through it. it's all based on that real simple model. And in fact, that's what we start with. Let's just go ahead, hit Shift Enter. We can just plow through these things. And here's what we just did before. So now in this particular case, our job is, and it's already done for us, is to say, hey, we want to put a well in the middle of this cell and run the model. So this sort of sets it up for us. We say this is how big we want our domain. Let's say we want it to be 150,000 feet wide and 150,000 feet north and south. We're going to divide this domain into 21 by 21 rows and columns. We calculate our row and column spacings. We're going to use one layer. We have a top and bottom, just all, sort of cartoon style parameters. And we've created some information then that we can pass in to these FloPy objects that will then allow us to customize this model and make it something that we want it to be or want it to represent. So now let's go ahead and run this one. So here now we have this very simple domain. We put a well right smack dab in the middle. And we ran it. Nothing too special, but the one thing that I'm going to say this because it's so important to me and things that I do, both in real world applications and a lot of the MODFLOW testing that we do, is it's really nice to have models that run fast. As a consultant now, I see a lot of models that run very slow, and I'm a big proponent of calibrating even and making models, getting models to run quickly, working out a lot of the kinks, and then if necessary, add resolution both temporally and spatially. But in this particular case, we can change this from 21 rows and columns to be, let's say, 201 rows and columns. And if we do this right, we can very quickly change the resolution on this model from being a simple 21 by 21 model to a 201 by 201 model. And because everything is automated, and if we built this in as an objective, this capability to build models sort of from native information, we have a lot of control now to get our models up and running, working, maybe giving good results before we go on to harnessing ourselves with these excruciating runtimes. Just something to think about. It requires work up front, but I'm a big proponent of these quick running models, at least initially. So I changed it back to 21 by 21 for us to keep moving forward. So now let's make this a transient model. And again, this is a MODFLOW 6 model. And so I know many of you are probably familiar with MODFLOW Newt, MODFLOW USG, and the concepts are similar. The packages are a little bit different. But this is a MODFLOW 6 version of something you could also construct just as easily with any of these other MODFLOW flavors. In MODFLOW 6, we create the time discretization package. We create what we call the period data. We say we're going to have a period length of 100 days. We're going to break it up into 100 time steps, and we'll have a time step multiplier of 1, so it'll just be evenly spaced time discrete time steps. We can run this. Now we see 100 time steps. We're plotting the last one. And I think FloPy has an example or a capability for going in and grabbing time series or getting back an array that has the time and then head at specific locations. And this is just an example of what that syntax looks like. We can get back an array that we can easily plot to show drawdown or head. What is this? This is actually calculating drawdown. This is drawdown. we're taking the head at the very first time step minus each consecutive head value and plotting that with time. So you can see this, the drawdown increases with time at our well, row, and column location. And I know I'm kind of going through this pretty quickly. It's more to demonstrate these concepts. There's a lot of syntax in there, but hopefully this sort of workflow, the ideas here are coming through. And then now let's do it again with that same set of wells. I think this is the same set of wells from that we used in that Tice example from before. We can create a list of these wells. See, actually, before we run it, and we did just run it there, we're doing something else here. We had this list of wells. Now we've gone through this well list, and what we've done is we've taken this model grid object, which is something that FloPy sort of creates in a lot of cases under the hood. And it allows us then to do spatial intersections with our model grid. So we can now find the row and column location of each one of these wells. And then we can build this list of our well information, which is what FloPy needs. So FloPy needs the layer, the row, and the column in zero-based, and the pumping rate. And this is the information it uses to create the well package. If we want this stuff to change with time, we would have a new list for each time. But this just shows programmatically how you can generate these things. In our case, using a list of wells, but these wells could come from a shapefile. They could come from a text file, an Excel workbook, whatever form you have the data, we can generate and intersect and figure out where these wells are and build that into our modeling process. So I can run this again, but now we have all these wells on, and we get this result. And it's coarse, but because we've built in this capability to change our grid very easily, it's quite simple to go back and change that. I'll do that real quick. We can go back up. Where do we specify the row and column? Let's just make it 100 by 100. And I'm sure this is and I can just say run all cells, and it should go through, run the entire notebook from start to finish. And wherever we've used rows and columns, now if we set things up, it's taken longer to run. Now we get a much more refined map of our drawdown. So these are the things that sold me on this workflow when I started, recognizing what Python could do when combined with modeling. Now you have this notebook, you can go back and run it. I think we've created different versions of this notebook, for the last decade, and it's straightforward to get it back up and running again. And it's a really nice way to sort of have a collection of problems and demonstrate groundwater flow patterns. Okay, I'm gonna keep going. Any other questions there? I'm gonna take a quick look here. Yes, I see one. Two questions here. One, in your experience, what is a quick running model time versus one that is excruciating? So I would say I love models that can run in less than 10 minutes. I would say that's tolerable. If they run in less than, say, 4 to 8 hours, we can probably calibrate them with PEST. If we have extensive computing capabilities where we can run hundreds of models at a time. But if we have models that take a week to run, it gets really difficult to work with them. So there's just, in my opinion, there is just so much that you can do with the modeling process with coarse representations, so much of the process is just finding mistakes in data, getting things working properly. And if you can do that with something that runs fast, once it's running properly, add resolution as needed. Another question, is it possible to have finer discretization in the vertical direction for layers for the 3D domain? The answer is absolutely yes. It's not a freebie though, you have to build that into your script, and we typically do that. So you have to somehow provide the number of layers then to be something that's adjustable by you at the beginning of the script. So you have to anticipate, hey, I'm going to want to split my layering up. So you might have to read it. You might have to have information on tops and bottoms, but then you can say, all right, I want to split that. I want to split one of those layers or all of those layers into 10 layers. And so, yes, you can build that, but you have to sort of set it up to handle that. But that's really where the power comes in. And it's something that we don't often do as groundwater modelers. I guess I've always been told I should do it, what's called a grid resolution study, right? You should start out with a coarse representation and continue refining your model until the result that you're interested in stops changing with increased resolution, right? That means you found the resolution that is relevant for your particular problem. Now, I recognize that's very difficult to do in practice, but I think these workflows do take you a step in that direction. Okay, let's save this. Save notebook and close, shut it down. Okay. How about I'm going to switch over. Now we've run a few of these in this Jupyter notebook. I'm going to switch over to my Mac and just show you these things in VS Code. VS Code is a free development environment. And so now I'm on Mac instead of Windows, and I have VS Code running. We have these same notebooks, and I'm just going to open up the Toth. And I don't know if you guys can see that. Let's see if maybe I can, hopefully that's okay. But it works pretty much the same. Again, we hit Shift Enter to run a cell. This is kind of a cool problem. It's one of our FloPy examples, but I'm sure everybody's heard of the Toth problem. We're groundwater people. We can build this simple Toth model. We can, again, now we've put in the size of our domain. We've allowed this to dynamically change the layers and columns in this particular case. We set up our Toth parameters. So we put in a water table on the surface. This is a 2D cross-section model. We can put a fluctuating water table on the top, which we use constant heads to do that. We can build we build our FloPy representation of this model, which FloPy converts into MODFLOW input files. So we built this thing behind the scenes. What's happened is it's set up. Let's see, we created this EX04 folder. It doesn't have anything in it yet. We can write the simulation. When we hit write simulation, these are the files that it generated for our Toth problem. We can go in and look at them. This is the MODFLOW 6 discretization package. This is what FloPy is writing for us directly. But instead of us putting all this stuff in the right place, FloPy knows how to write all this information and puts them in there. We can use constant values, or we could specify arrays if we wanted. I'll show an example of that, hopefully here. We can run the simulation then, and we can load the output. And there's a number of things that are going on here that you'll see just very briefly. But if we want to see the stream function, we can calculate the stream function, which shows flow lines. This is just a few lines of Python code that calculate the stream functions. And then lastly, we can end up with a plot that looks like this, where we have constant heads assigned to our top layer. Again, this is cross section. We're specifying the heads in that top layer, which are constant heads, and we're generating a Toth flow system where we have these local, intermediate, and regional flow systems. And because we've made this, because we've set this up to be dynamic, let's try 400. And we won't run with this. We can say run all. Hopefully there we go. That's with 400 and 200 rows and columns. And we can get a very crisp and fine resolution of the Toth problem. So that's pretty cool. And really just with a little bit of FloPy and Python code, we're able to generate this stuff. All right. There is a question about what is the advantage on groundwater vistas. That's a great question. I'm a big fan of groundwater vistas. I like to use it to quickly look at models. You can see to quickly open up a model and look at it. You can do that with Python and FloPy, but you've got to be very proficient with Python commands. And it's not point and click. There aren't easy menus for showing boundaries. You have to write the code itself to plot the boundary conditions or to show what you want to show. You have to generate that. You have to write that code to do it. Pointing and clicking and check boxes are really nice when you want to do something quickly. In my opinion, it gets a little bit harder to automate things when you have to do things over and over again. That's where the GUIs sometimes are less efficient, though I think there are also ways to automate some of those tasks as well. There's a question about have many regulators who will they accept FloPy files in lieu of model files built by a GUI? I would say absolutely yes. I don't think there's any downside to that. The files are the authoritative source in terms of what MODFLOW is doing. So in my opinion, and as a MODFLOW developer, I would say the files themselves, really are the important part of a MODFLOW model. What you do in the GUI is important, but the GUI itself is translating things into the model files. It's not always exactly clear how that's done, but the model files themselves are really sort of the anchor for the results that you're getting from the model. Question, is FloPy updated with all transport packages across MODFLOW 6 and others like MODFLOW USG? So for MODFLOW 6, all of the transport packages are fully supported and you can use them right now. As we release them, FloPy is ready to go. MODFLOW USG, it's been a little bit of a delay in how quickly we can support some of the changes in MODFLOW USG. So we're working on that, and we have some people that are helping out with that. But the interface between FloPy and MODFLOW USG is lagged by a little bit, whereas the interface between FloPy and MODFLOW 6 happens instantly based on how we do things. So that's why there is a difference between the support levels for the two. All right, so I'm going to close this. We're at 12:35 right now, or I guess 10:35 your time. Let's go on to an island case. Real quick on this one, let's just run this one real quickly because I want to make sure to show you all of the different ones, in particular this last one because it's a California model. But here's just another very simple example. I'm just going to hit run all, and it's just going to go through, and this is just some model domain. Let's say it's an island. We can create a model grid. We do this up front because then we can do some intersection capabilities. There's a little bit of code here to show how we might identify cells based on that polygon. We can say, okay, these purple cells, we want them to be out of the model domain. The yellow cells, we're going to use constant heads, or I think that's what we use for this particular case. But we've used the intersection capabilities in FloPy to figure out, based on this polygon, or it could be a shapefile, or it could be a GeoPandas data frame, could be a variety of different things, figure out which cells are in our island and which cells are outside of our island, and we can assign boundary conditions accordingly. This intersection capability allows us to build models from scratch using native information. And I would say that the capabilities that we have in FloPy and in Python are really extremely fast. That's an advantage of doing this with FloPy. I've been a big fan of ArcGIS, and I used to do all my processing in ArcGIS. It can be pretty slow. And a lot of Python stuff, I would say, is extremely fast, especially working with rasters and images and things like that. You can do some processing, orders of magnitude faster than going to a very powerful GIS, but perhaps not optimized for what we're doing. In this case, well, I guess we built the model, we ran the model, and we made a plot. I think we have recharge in this particular case. Now so we made a map view. We have a plot of the velocity vectors. Again, water table contours. The blue is showing constant head cells. The gray are inactive cells. We have flow from the center of our island outward. And FloPy also has capabilities for making cross sections. So these are just some built-in capabilities. We can create some really nice, I would say, figures with FloPy, both map view as well as cross-section view, and you're going to see a few more of these. Save that. Question, any plans to add flow vector arrows to MODFLOW USG cross-sections? See, that's a good question. So I'd have to talk to Sarab about this, who's actually presenting later today. Maybe you could ask him. But in MODFLOW 6, we've added the capability to export velocities or specific discharge for each cell. So internally to MODFLOW 6, we're calculating flow directions essentially, and we write those out. And so FloPy is very easy for FloPy to draw those. It'd be nice if MODFLOW USG had something similar. And I don't think that's in there, but if it were, that would be something that FloPy could support as well. And I think the GUI developers would like that as well. It may be that they're in there, but I'm not sure about that. But good question. All right, let's go on to the next one. The Henry problem, and you can probably tell I've been I guess in California, saltwater intrusion is also a big deal. In Florida, it was something I worked on for a long time, particularly with my work with CWAT, and our latest work with MODFLOW USG and MODFLOW 6 and the ability to simulate saltwater intrusion. Well, the Henry problem is a nice, simple, it's this small little box problem where we simulate saltwater movement just in a little box. And in this particular case, we are developing a MODFLOW-6 model that has both a flow model, a transport model, and buoyancy effects that are active. And we'll take a look at that in 1 second. But here we can specify sort of our parameters that we want to use, our variables that we're going to use to build this model. And again, we can change these things. We're going to construct a simulation. So the simulation in MODFLOW-6, the simulation is what holds multiple models. In this particular case, we have the simulation has 2 models. It has a flow model and it has a separate transport model. And they're actually very independent. We build them separately, but we allow them to communicate, or MODFLOW allows us to have them communicate so that we can take the flows from the flow model and pass them to the transport model. And also we can take the concentrations from the transport model and use them to calculate densities for the flow model. So there's this sort of two-way feedback that's happening. Here we're creating a flow model, and here we're creating a transport model, and we're adding them to the simulation. And I know we're going through this very quickly, but conceptually that's what's going on here. And we're building a set of packages for the flow model and a set of packages for the transport model. We're creating an exchange package, which tells MODFLOW-6, hey, we want the flow model and the transport model to be able to share information. We're writing the data sets. So now if we go and look, I think this is, what are we on? Exercise 6. You can see we have flow packages. As an example, we have a flow name file where we have a discretization, NPF, we have GHB, probably things you're familiar with. But we also have a transport name file. We have a discretization. We have this mobile storage and transfer initial conditions, advection, dispersion. So we have a transport model. We can run the simulation. There you can see it running. You can load the results, essentially getting back all of the concentrations for that whole simulation. I think this just shows one of the plots. Again, this is a cross-section model. We have freshwater flow on the left side, and we have a saltwater boundary condition on the right side. I guess maybe based on Henry's work in Florida, the ocean is on the right. Maybe we should flip this for the California case and put the ocean on the left. And here we can now create an animation just like we did before with this code to show, and this is, I think we're only saving a few frames. Creating animations can take a little time, and we can plot what happens. We start the box with salt water. We pump in some fresh water on the left, and we get this interface to form. And if we wanted, I think we're showing up here, that's pretty coarse. We're showing every 50 frames. 10 was kind of short. Let's see if we can do every 20 frame. Every 20 time step. Let's see how long that takes to create that animation to get something a little bit smoother. Go, let's see what we got there. So it's a little bit slower. And you see that saltwater wedge form at the base of the aquifer because of the density difference, because saltwater is 2.5% more dense than freshwater. We get this particular flow pattern. All right, we've got 2 more. This next one, this is another saltwater problem, sort of, but it's based on the Henry problem, but it's time varying. I'm going to call this, it's called our title problem. Back up to the top. I'm just going to go ahead and run this because I do want to get to the last problem. See if we can run this. Just going to hit run all. And this one takes a minute to run. But this is the Henry problem, except what we've done is we've put a tidal boundary on the ocean side, and that tide goes up and down. And because the tide is going up and down, and we have a sloped seafloor, because the tide is going up and down, we have the interface sort of sloshing back and forth in this particular simulation. And really, we've had to do this somewhat quickly, and we're not going to get into any of the details of this particular model, but like the Henry problem before, it's a flow model and a transport model coupled together, and we're generating the interface, and we're generating the coupled flow and transport model. And here, if we run this, so now what we have is this is a cross section again. We have a sloping seafloor. We have the tides going up and down. We actually have quite a bit going on in this particular case. These are salinity contours where blue is more or less fresh, down to red, which is more or less seawater. And we have this tide going up and down, and we see the interface sloshing back and forth. Highly exaggerated for this small box, but you can see how this might be upscaled for real models of coastal areas. And we can see one more animation at the bottom here. This is just another plot showing something similar, where we're seeing also the velocity vectors. One of the nice things that the MODFLOW-6 and also MODFLOW-USG offer is we're using the Newton formulation for this for saltwater intrusion. So you can simulate dry areas. CWAT, that was always a problem with CWAT for saltwater intrusion modeling. It wasn't as stable as some of the newer codes. So that's why, MODFLOW-USG and MODFLOW-6 are certainly recommended for saltwater intrusion models these days. Okay. There's a question about, have you ever worked using different time units between the flow and transport model, and how does FloPy handle that? So that's a great question, and that's somewhat complex. So one thing you can do with I think with MODFLOW-USG and MODFLOW-6, you can run a flow model first. It could be a steady state flow model, for example, which is a common case for solute transport type examples. You can run the flow model first, and then you can go back and simulate solute transport reading results from a previously run transport model. So you can do that. Alternatively, if you have to run for some reason, and there are different reasons like variable density, if you have to run them together in the same simulation, then you have to use the same time step in the flow model and the transport model. We tried initially when we developed MODFLOW-6 to not have to have that restriction, but it turned out just to be too complicated to allow different timing, inner time stepping within the different models. Something we might evaluate again in the future, but not at the moment. Another question is there a Python code for MODFLOW-6 for a zone mass budget, or maybe for USG? The answer is yes for both of those. MODFLOW-6 comes with a version of zone budget for it. That zone budget for MODFLOW-6 works on all of the different budget files. It has it works on a flow budget file, as well as a transport budget file, as well as budget files for like multi-node wells and other things. So it does some cool things that you might appreciate. MODFLOW-USG also comes with something called ZoneBudUSG, so you can calculate zone budgets for MODFLOW-USG as well. Those are separate executables that come with the codes, and there are some FloPy capabilities for interacting with those, but it's not always necessary, because those programs write CSV files that are pretty simple to load. with just standard Python and process them that way. Okay, we have one more example, and this is not one that you're going to be able to run. It is, so I was looking for models to use that we could just load and maybe show a few things. And I found the best one I could find was this Los Angeles coastal plain model. It's a MODFLOW-6 model. And I was just looking for something that wasn't too big and we could maybe make some maps and show a few different things. I didn't get as far as I would have liked to on this. I don't have the results. I just have the grid, but we were able to load it and look at some of the input parameters and plot things on a map. For this one now, we're gonna try to do some better things in terms of geospatial information. So if you're a GIS person and use Python, maybe you've heard of contextually or folium. These are map capabilities that allow you to create geo-registered maps. And this is some nice, it allows us to interact with these models and put them on a map and do some cool things. So I downloaded this LA coastal plain model from the USGS website, and I just unzipped it into its own folder and I called it LACP. That is not in this repository, but if you wanted to get this to run, you would want to unzip it and put it sort of in this folder right next to the notebooks folder. And in there, you can see the MODFLOW input files. And if we just sort of step through this, see, step through this and run these. So there's one of the things that I've done here up front is I've just added a simple function to give us back this FloPy model grid, which is something that's geo-registered, but it has the row and column spacings and allows us to put our model on maps in real world coordinates. This model was developed using UTM coordinate system and the model's in feet. So we had to do some conversion, and that's what this model grid does. It allows us to show us the model on this particular coordinate reference system. You're probably more familiar with this than I am, the details here. And we're also accessing an Esri base map, so we can show there's different tile servers for showing base maps under the hood, but we can drop our model grid and our model features on these different base maps. So one of the first things we're going to do here is just load this model. So MODFLOW-6, you provided where the model is. In our particular case, it's in this LACP folder, which is just up one and in LACP. We create a new simulation by loading the model that's there. We're changing into that directory and loading that model. So at this particular point, sim has that entire model loaded into FloPy memory, essentially. It's all in memory. And so we can access different things, like in this particular case, there is, excuse me, there was a single model, the LA Basin model that's in the simulation. We can pluck out the groundwater flow model. So what we're doing is say, hey, give us back the LA Basin model, and we're going to put it in GWF. We can see what packages are in that model. Here's a list of packages. And for any of these packages, then we can burrow in and pull out the data for those packages. So in this particular case, we're getting the hydraulic conductivity. We're saying, hey, get the NPF, the node property flow package, get the hydraulic conductivity, and get data, get it back. And we're going to just showing the min and max values. We could, however, though, if we wanted to see what that is, we could say, just so you can see HK. HK is an array. It's a three-dimensional array. We're just seeing ones. It's only because we're seeing the outskirts of it. But because it's an array, we can do these other things, min, hk.max. So we can essentially get at all of the data that's in the model for any of the packages. FloPy has easy ways to plot things. So the discretization package itself has top. We can just say gwf.dis.top.plot, and we get back a plot of the top surface. And we should have color bars here, and we can add them, but we're not going to due to time constraints. We can also plot a whole package. In this case, we're going to say groundwater flow model.dis, the whole discretization package. We can say dot plot. And FloPy will go through and it'll look for everything in that package that it can plot. And in this particular case, it found top, bottom of layer 1, bottom of layer 2, and it just, spit out all these maps of whatever it can find in there. iDomain, layer 1, 2, 3, 4. So it's a real quick and easy way to make maps of a model that you may have loaded. There are also these more customizable ways to plot things. FloPy has a plot cross-section capability, so we can draw a line through our grid or pick a row or pick a column. If it's an unstructured grid, we can draw a line and it'll draw a cross-section for us. Or we can plot our different layers and drop anything we want on these plots. Anything you can plot with Python, we can add to our FloPy plots. And so here's just an example showing GHBs and drains. If we wanted, we could add the hydraulic connectivity and so forth. And lastly, I'm just going to conclude with we can now also work more seamlessly with GeoPandas data frames. So GeoPandas is just a nice way to work with spatial data. So we can get back a data frame of our model grid. I'm not going to plot it because it's so dense in this particular case. But once we have a geodata frame, we can easily tack information onto that. Our iDomain or our hydraulic connectivities. And let's just sort of go through these last little bits. We can very nicely, because it's a GeoPandas data frame, we can drop these things now onto interactive maps where we can zoom in, and we can actually do this with a model grid. But here we can see, using an Esri tile server, where whatever it is we want to show. And then lastly, we have these two other maps on this using contextually, where we can make these static maps that show our model grid and model features and anything else we want to do on maps using different backgrounds. And here's just an example showing our model grid on one of the default map tile server or on an Esri tile server. And so with that, I think I'm really sorry I used up the whole time. I do see one other question here. Can FloPy also simulate river runoff with interaction to groundwater? Yes. There's the stream flow routing package that the different versions of MODFLOW come with, and you can build those data sets. So yes, you can do that. There's a question is can FloPy and MODFLOW simulate freezing conditions such as those in the polar or Arctic environments? At the moment, no, you can't do that. Another question, there's a version of USGS code called Sutra Ice, though, which allows you to do that. Can you point us some additional training tutorials? There's a lot of stuff on the web. Maybe I'll link to a few things on that FloPy on that repository that I created. There's tons of stuff. Sarab is going to show some other ways. You can use Chat GPT now or other AI code to help build a lot of this. So yeah, I think all the stuff is available online. Everything you've seen today is available online. All these examples are available. And so with that, I think I'm gonna close it up unless anybody has any questions in person.
I don't see any other questions popping up in the chat, but thank you so much, Chris, for today's session. We really appreciate it. And that ends today. Thank you, everyone. Goodbye.
All right.